Hello everyone. The topic of the presentation is Google File System and our team members are Nandini, Kailashnath and myself Prayag. So before moving to the Google File System, what is file system? What is distributed file system? So file system are the abstraction that enable users to read, manipulate and organize the data. Typically, the data is stored in units known as file in a hierarchical tree where the nodes are known as the directories. The file system enable a uniform view independent of the underlying storage device, which can range between anything from floppy drive to hard drive and flash memory card. Since file system evolved from standalone computers, the connection between the logical file system and the storage device was typically a one-to-one mapping. Even software RAID that is used to distribute the data on multiple storage devices is typically implemented below the file system layer. Now, what is the distributed file system? During much of the 1980s, the people that wanted to share file using a method known as sneakernet. A sneakernet is the process of sharing file by copying them onto floppy disks, physically carrying it to the another computer and copying it again. As computer networks started to evolve in 1980s, it became evident that the old file system had many limitations that made them unsuitable for multi-user environment. At first, many users started to use FTP to share file. Although this method avoided the time-consuming physical movement of the removable media, files still needed to be copied twice, once from the source computer onto the server and a second time from the server onto the destination computer. Additionally, user had to know the physical address of the every computer involved in the file sharing process. So as a computer companies tried to solve the shortcoming above entirely new distributed file system such as Sun NFS, Sun Microsoft Network File System, Andrew File System were developed. But there are a few issues associated with the distributed file system. Naming. Is the name access independent or location independent? Location transparency make it possible for the client to access the file system without knowledge of where the physical files are located. For example, this make it possible to retain path even when the server are physically moved or replaced. Another issue is that migration and directories. How the directories are handled? Can files migrated between the server machines? So in FTP file is migrated, but user must be aware of that. While in NFS, it must change mount point in client machine. Another issue associated with is file locking. Does the system support file locking? What type of file sharing semantic are supported if the two processes accessing the same file? Another issue is caching and file replication. Now, caching should be implemented either client side or a server side, and how it works to reduce the complexity to also a major issue in distributed system. Scalability and security also there is a major challenge because in NFS a server only authenticate based on ID. So later on the security version is improved in NFS version 3, 4 and later part, but it is a major issue how the scalable system we can develop, and state and stateless homogeneity also is a major issue. So this is the commodity cluster and this is the commodity hardware that used in 90s and to build a large scale distributed system. In any distributed file system there is a two bottleneck, one is network and another is storage. So the commodity hardware, it is a device or a device component that is relatively inexpensive, widely available and more or less interchange with other hardware of its type. Unlike purpose-built-in hardware designed for a specific IT function, commodity hardware can perform many different functions. Commodity hardware is usually low-end, broadly compatible and can function on a plug-and-play basis with other commodity hardware products also. Now, commodity computer, for example, is a standard issue PC that has no outstanding feature and it is easily available for purchase. Commodity hard disk can be configured using a redundant array of the independent disk RAID for a fault tolerant, and generally the commodity hardware can evolve from any technological mature product. So this is the bottom slide. It is discuss about the cluster architecture. There are multiple switches and multiple CPU, individual memory and individual disk described there. In above slide, the commodity cluster is a today's present world cluster that multiple racks is associated. It is used in data center, and left hand side it is a older system that used in 1980s and 1990s. So another issue is that why not use an existing file system? So at the time before Web 2.0 came, there is no file system which can handle a large amount of data. Inside the Google's world of database, there are a lot of large data available. So as a consequence of this service Google provides, Google faces the requirement to manage large amount of data, including but not begin limited to the crawled web content to proceed by the indexing system. So that the Google's problem are different from anyone's else file system. It is generally used for own application and own functionality. It is used for internal Google's application data center. So the block size of Google file system will require more amount of data in comparison with traditional file system. It is mainly designed for various large distributed data intensive application. It provides fault tolerant while running on inexpensive commodity hardware, and it delivers high aggregate performance to a large number of clients. Now major objective is GFS is it is a scalable distributed file system for a large distributed data intensive application, and main objective is to provide performance, scalability, reliability and availability in a distributed file system. In the initial days of the search engine like Yahoo, which were being used all over the world, now this paper gives an answer as to how the Google search engine was able to achieve its objective to stand against all its rival and later on become the most widely used search engine throughout the globe. The ever-growing use of technology in people's daily lives has brought the need to manage big data efficiently. Now Google has put effort to provide a distributed system, also allowing them to scale up their system when more data is to be stored, large scale data processing along with the ability to cover up during the critical situation and hardware failure also. The GFS is the reason for the success of the Google and other services. There are some assumptions while designing the system. The first of all assumption is that system is built from many inexpensive commodity components that often fail. Now component failure are the norm rather than the exception that the file system consists of the hundred or even thousands of the storage machine built from the inexpensive commodity part. The quantity and the quality of the component virtually guarantee that some are not function at any given time and some will not recover from their current state of failure. It is caused by some application bug, operating system bug, human error and the failure of the disk, memory or maybe networking error or suppose a power supply stop. So therefore the constant monitoring, error detection, fault tolerance and automatic recovery must be integral to the system. The system store a modest number of large files. Now they assume that files are huge by traditional standard. Multi-GB terabyte files are common. Each file typically contains many application objects such as web document. When we are regularly working with fast growing data, set maybe in terabytes, gigabyte, comprising billions of objects, it is unwieldy to manage billions of approximately KB size file even when the file system could support it also. So here small files are supported, but it's required to optimal manner. It is mainly designed for the large file. The workload preliminary consists of two kinds of read, large streaming reads and the small random read. In large streaming read, individual operation typically read hundreds of KB, more commonly 1 MB or more. Successive operation from the same client often read through a continuous region of file. Now a small random read typically reads about few KB at some arbitrary offset. Performance conscious application often batch and sort their small read to advance steadily through the file rather than go back and forth. The another workload also may have large sequential write that append data to the file, and once written it modified later on also. And small write are arbitrary position supported, but it is not efficient. It is generally efficient for large streaming read data and large streaming write data also. Now the designing of the GFS. The GFS cluster consists mainly three components: a single master, multiple chunk server and multiple client. Multiple standalone and independent cluster are together make a GFS. Now each cluster include a master and multiple chunk server. cluster accessed by the multiple clients, and it can be possible that chunk server and client run on the same machine also. So here are the client, master, and the multiple ABC is the multiple chunk server. Now a GFS cluster, in a master, the files are divided into fixed size of chunk. Example, each chunk is identical by immutable and globally unique, a 64-bit chunk handle assigned by the master at the time of chunk creation. So say for example, here is the file about hello, and here is there some content in it, and it is divided by multiple chunks, which is the size about 64 MB, and these chunks are replicated on the different chunk server simultaneously, and by default the replication factor is about 3. So we can customize the replication factor also. So this hello.c file, say for example, it's divided in the multiple chunks 1, 2, 3, and these chunks is also replicated on the different chunk server. Chunk server store the chunks on the local disk as the Linux file and read and write chunk data specified by the chunk handle and byte range. The master maintain all file systems metadata. Now GFS client code link into the each application, that's file system API, and communicate with the master and chunk server to read or write data on behalf of the application. Now client interacts with the master for metadata operation only, but all the data related communication goes directly to the chunk server. Now in neither client side or the chunk server side, caching is not implemented. So it is a beauty of the GFS. Client never read and write file data through the master. Instead, client asks the master which chunk server is should contact. It catches this information for limited time and interact with the chunk server directly for many subsequent applications. So in the client itself, the GFS client library is available. It will use the fixed chunk size to translate the file name and byte offset specified by the application into a chunk index within the file. Then it sends the master request containing the file name and chunk index. Now client sends the request, hey master, please give this file name and this chunk index. Now master will look at that namespace where the file is located, where the chunk is located, and after finding this in master metadata, it will give reply to the client, hey client, this is the chunk handle and this is the chunk location. Now the client send a request to one of the replica, which is most likely the closest one. It will decided by the based on IP address, so which is closest replication chunk server is available to the client, and the request specify the chunk handle and the byte range within that chunk. Now further reads of the some further required further chunk server communication, there is no requirement of that connection. The once the TCP connection established, it is extend TCP connection, and all the chunk server data will operate, read or write or append operation will happen to the client, which is described in fourth block chunk data. So that the master interaction is minimal, only that where is the location, where is the file, that kind of master interaction is happen between client and master, and all other data communication happens to the client and chunk server. Now in that master and chunk server communicate through heartbeat messages. Master send the heartbeat messages either for startup of the chunk server or periodically the chunk server master send heartbeat to the chunk server, and the chunk server will give reply that heartbeat messages. This is the chunks, and these are the version number updated chunks, and these are the orphan chunks, these are the garbage chunks, and what kind of chunks is available, what kind of access control is there. So all the data, metadata is contained in the chunk server metadata also, and it's contained metadata in master metadata also. So this is the GFS architecture described in the paper. So that a GFS client will interact with file name and chunk index. Now GFS master will look into the directory and find that chunk location and give the chunk handle and location. Then the client interact with the chunk server. through that it is a multiple chunk server, and it is all Linux system, and then it will chunk server reply to the client through the chunk data. So here are the chunk server and different file, a different chunk server and different file, different chunk is located. Say for example, file 1 chunk 2 is located in chunk server 1, chunk server 2, and chunk server 3. By default it is application factor 3. If it is one downs the chunk server, or maybe 2 chunk server is down, then one file is at least available, and at that time the master through the periodical heartbeat know that there is only one chunk server, one chunk is available and other 2 is down, so it will quickly replicate this chunk as much higher rate, and that kind of operation is available. And one other important thing is that shadow master. So in shadow master, what happens when the master maybe goes down or maybe crash, so it is hardly, maybe it is a few MB file of metadata, and it recover from metadata, it hardly take 2 to 3 minutes. So in that 2 to 3 minutes, when multiple client approaches that master, the shadow master is available, and in this shadow master, through that shadow master, those client read operation is happen successfully. Write operation is not successfully, but read whatever read operation, it will handle by the shadow masters. So the master maintain all the file system metadata, and it include namespace, access control information, the mapping from file to chunk, when chunk created, which chunk server is available, where the network bandwidth is low and the load is low, so that chunk is created, the version number is also updated, and all other the chunk related activity master give the grant, and it store the metadata of the system. It also manages the chunk list management. So whenever the client request to the write file, the master allow that chunk that hey client, go to that chunk and write to that primary chunk. So list management is also handled by the master level. The garbage collection, obviously when the different chunks are available in the chunk server, there are some chunks that is a successful operation is not happen, so it will be a garbage. So periodically once identified that is a garbage, so after it will first of all it is inside it is in hidden file, and after 3 days the garbage collection periodically remove that storage. And master obviously periodically communicate with the each chunk server in heartbeat messages to give it instruction and collect its state. Now chunk server. Chunk size is one of the key design parameter, and it has 64 MB, which is much larger than typical file system block size. Now how they decide 64 MB? It is a multiple experimental came, and then they decide about 64 MB file. And each chunk replica is stored at a plain Linux file on a chunk server, and it extended only as needed. Now bigger chunk size has the advantage is that it reduces unnecessary overhead with master. In a large chunk, client is more likely to perform many operations on a given chunk and extend persistent TCP connection also. It reduces the size of the metadata stored on the master. Operational log. The operational log contains a historical record of the critical metadata changes. It is central to GFS. It is not only the persistent record of the metadata, but it also serves as a logical timeline, and that defines the order of the concurrent operation. File and chunks as well as their version, all the uniquely identified by the logical time at which time they were created, and it's replicated on multiple remote machines. So in case of the master will fail, quickly recover those state. The master recover its file system state by replaying the operational log, and the master checkpoints its state whenever the log grows beyond the certain size. Usually the master metadata contain 64 MB or 48 MB file. So when it crashes, it requires 2 minutes to recover its original state. So keeping operational file small, it will help to the faster recoverability. So that's it from my side. Now I will invite my teammate to discuss further. Over to Kailash Nath.
So this is Kailash Nath here. We'll be looking at how mutations are enabled in GFS. So a mutation is something that modifies an existing chunk or a file. It could be a write or an append. We'll be seeing what the difference is between write and append in the next slide. So as of now, anything that modifies the existing data comes under mutation. So that is one issue with mutation. Since we have multiple chunk replicas, multiple clients can write to multiple chunk replicas at the same time. So this causes an consistency issue. The client replicas might exchange the data returned to them between them, finally resulting in the same data being present in all the chunk replicas but in different order. So in order to solve this, the authors have used something called chunk lease. Chunk lease is nothing but designating a particular chunk as primary and letting it decide in what order the mutations have to be done. So the master contacts a particular chunk replica and designates it as primary. So when different data are coming to primary, the primary ensures that the data are being written in a specific order at all the chunk replicas. So at any particular point of time, if a client is writing data to a particular chunk replica, the chunk replica has to contact the primary and get the order in which it has to append the written records. So this is one aspect. The second aspect is the decoupling of the data flow and the control flow. So control and data are completely decoupled. So if I write a particular amount of data to a particular chunk replica, first I'll initially pass all the data and then tell the primary of the particular chunk replica on what to do, whether to write or append. So the uh, advantage of this is uh, we can schedule the data flow on the network topology in a way that is least expensive, regardless of which chunk server is being designated as the primary at the particular moment. So we do not have to worry about the primary, and we just use the most inexpensive part to pass the data. So now we'll be looking at two type of mutations. One is write and the other one is record append. So if a particular client wants to update an existing file by writing data to it at a specific point, it uses the write command, because this command not only passes the data but also tells the chunk server on where to write this particular data that was passed. In case the client is not bothered about where the data is going to reside in a particular chunk replica, it just uses record append. One more feature of record append is that this is atomic in nature. So whatever data is being received from the client, it is written in one go. So this is one of the feature. So we'll be diving a bit more deeper into record account here. So let's say the chunk server receives particular data, and let's say the chunk is already 44 MB full. So the chunk size, as we have already seen, is 64 MB, and let's say 44 MB is already occupied, and the data received is 5 MB. So the data received can be easily fit into the existing chunk. So the chunk writes the data atomically, and the primary, as we have seen in the last slide, tells the other replicas to do the same thing. So if say we get a data that is let's say more than 20 MB, that is the free space in the chunk left. Let's say it's 25 MB. We see that this data cannot be written in the chunk at one go, because the maximum chunk size is 64. So if so, it is the responsibility of the chunk to pad the existing chunk with, let's say, zero or null values, tell the other replicas also to do the same thing, and tell the client that you have to create a new chunk and then write the data to it. So this can result in one issue. One is fragmentation. Let's say we there is a chunk which has only 1 MB of data in it, and then we the client asks us to write something that is 63.5 MB big. So now we see that this 63.5 MB cannot be fit into the remaining space, and now we have to create a new chunk. So this can cause a lot of fragmentation. So in order to stop this, record append, the size of data that can be written through record append is being limited to 1/4 of the chunk size. So in this case, 16 MB. So now let's see step by step how the mutations are being implemented in GFS. So we have a single client here. a master, and yeah, let's assume each chunk has three chunk replicas, A, B, and C. So the master maintains this file to chunk ID mapping, and let's say the client wants to write A, B, C, D to this particular file, and let's assume there's only one chunk. So the client doesn't know where the chunk replicas are. So first it contacts the master and asks where the chunk replicas are, and also asks which chunk is being designated as the primary at this moment. So master gets this request and sees that there is no, it has not designated any chunk replica as primary. So it has two jobs now. One is to tell the client where the chunk replicas are, and also to tell which chunk replica is the primary. And before that, it has to create, designate a particular chunk replica as primary. So now it chooses B as the primary chunk replica, and then it tells the client that B is the primary chunk replica and the locations are ABC. So the client stores this particular reply in its cache. After this, the client has decided that the best way to, or the least inexpensive way to write data to all three chunk replica is to go through C and then B and then A. So the client sends the data to C. So C writes the data to its local LRU cache. Then it is the responsibility of C to forward the data to B. Now B writes the data to its local LRU cache, and then B forwards the same data to A, and A also writes the data to its cache. Now the client contacts the primary and tells that it's a write operation and not a record append. So now it is the job of the primary to tell both the chunk replicas what to do with the particular data that they are having. So now B takes the data from its cache and writes it to its chunk. And now it also tells both A and C to do the same task. So now A does the same thing and C does the same thing. So after all this is done, B then tells the client, so whatever you have asked me to do, I've done it. The both A and C have given me an acknowledgement that they have written the data successfully. So this is how mutations are done in GFS. See how consistency is being ensured when all of these mutations are happening. So the main thing here is the primary sends an acknowledgement to the client that all the operations were successful only when it itself has received acknowledgement from all the replicas that the data being passed was written in the specified order. So if say one of the replicas failed to write the data because it went down, so the primary does not receive this acknowledgement from the client chunk replica. So now what it does is it tells the client that the write operation has failed and asks the client to reinitiate the write operation. So this way, when data is not being consistent among the chunk replicas, we ensure that the data is being written again and consistency is ensured. This is one thing. As we have already seen, multiple reads are fine. So when there are different clients reading from a particular chunk, it isn't modifying any data, so it's fine. So, but when multiple writes are happening, there is a consistency issue. So we saw that this is being fixed by something called chunk lease, and we are designating a particular node to be primary, and we let the order in which the data has to be written to be decided by the primary node. So both of these factors ensure consistency. So next we'll be looking at something called snapshot. Let's say there's a file and it has a single chunk C, and client decides to experiment something with this particular chunk C, and maybe he's going to append or delete data. So now he needs a safe state to which he can roll back to when things go wrong in his experiment. So that's where snapshot comes into picture. So it's essentially a state where things were fine. So we'll see how the master and the chunk server work together to get a snapshot. Let's say a particular client is writing some data to a chunk C. So another client initiates a snapshot request. So master gets this snapshot request, and the first thing that it does is to stop the write operation by invoking the revoking the chunk lease it has given. So when the chunk lease is being revoked, data cannot be written because it is the duty of the primary to write the data or instruct the other chunk replicas and itself to write the data in a particular order. So write operations are stopped immediately. So the next thing that happens here is the master increases the reference count of the particular chunk. So reference count essentially means that someone is trying to take a snapshot of the particular chunk at this moment. So that's it. As of now, no fork is created. So when another write request comes to the same chunk, so master sees that the reference count has been increased by one, and now it is necessary to create a replica of this chunk or duplicate this chunk so that the data in this chunk is preserved and the write operations can happen in the duplicate chunk. So this the master is responsible for ensuring this. It creates a new client handle in the same server where the chunk replicas are held, and it instructs all the chunk replicas to transfer the data from C to C dash. So so this is how a snapshot is being taken. If suppose say the experiment goes wrong and the data, let's say C dash is being modified a lot of times, it becomes impossible to get back the same data that was initially in C dash. So this is where the snapshot that we took comes into picture. So we can roll back from C dash to C. So this is the use of the snapshot. We'll be looking at replica creation and rebalancing. So there are three scenarios in which a replica has to be created. So one is chunk creation. So when a client wants to create a new file, obviously a new chunk has to be created. This is one of the reasons that a replica is generally created. And the other one is re-replication. Let's say there is already a chunk replica and the chunk server that holds the chunk replica goes down. Now the master doesn't receive any message for a particular amount of time from the chunk server, and it gets to know that the chunk server has become unavailable. So now it's the duty of the master to contact another chunk replica and ask that to send data to another chunk server to re-replicate the chunk. So the other reason for re-replication is the client might purposefully increase the replica count that he wants. Let's say initially the client only wanted three replicas, and now an increase in availability is required. So he now increases the replica count to 10. So the master recognizes it and performs the necessary operations accordingly. So the other thing is rebalancing. So rebalancing is done to make sure that all chunk servers disk space is being utilized optimally. If suppose a particular chunk server uh, doesn't have many chunk, it means its disk space is not being utilized optimally, and let's say the other chunks are being completely overloaded, and the space available in other chunk servers are very little. So now rebalancing happens. The chunks from the overloaded chunk servers are now have to be pushed to the chunk server with low disk space utilization. So another case is to ensure a better load balancing. Let's say multiple reads are happening at the same chunk server for different chunks. So this puts a lot of load on the chunk server. Now, in order to ensure better user experience, we can shift some chunks from the chunk server to other chunk servers. This ensures that the better load balancing is being done. Now I'll be looking at what happens when a particular chunk or a file is deleted. So let's say the client contacts the master and tells the master that it doesn't need a particular chunk anymore. So instead of doing away with the chunks, what the master does is it changes the name of the particular chunk, and it also adds the timestamp of the client request. That is a delete request. So the chunk still resides in the chunk server and also in the master's records. So the master then waits for 3 days. And after 3 days, when a regular scan is happening, it notices that the file was deleted 3 days ago and it's not required anymore. So this master sees this and removes the file from the master node. But still, the chunks are still residing in the chunk server. So when the chunk server sends its periodic scan data to the master, it sees that there are some files that shouldn't exist. Now what the master does is it asks the chunk servers to remove these particular chunks. So what is the advantage of this? The advantage is that the client, the advantage of not deleting the file immediately is that the client might change his mind. He might come back and see that he actually needs this file. So this is something like a failsafe. So this the client may have deleted it unknowingly, or he deleted it and then he wants to reuse this file. So that is one thing. The other thing is if you see here, the master is not explicitly going to the chunk server and telling all the chunk servers to delete particular chunks. All of the deletion operation is being completely done using existing methods. That is using regular master scan, using the regular periodic chunk scan data that is being sent to the master. No new commands are being used here. So we are not using any special commands here. So that is also one more advantage.
Each day, huge quantity of data is produced by means of text, audio, image, and video format via many sources like social media, YouTube, websites, and so on. The most important part is storing this generated data in the file system. To store this intensive data, cluster based storage systems are required. HDFS and GFS are two major file systems which are used to store the data. Let's get an overview of GFS and HDFS and compare them. In 1990s, Google File System was developed by Google. There are thousands of storage systems utilized by the GFS from low-cost service components. These systems offer the many users petabytes of storage for their varied requirements. GFS design important aspects are reliability and scalability, file size from GB to TB, operations like appending file, random write operations to file, sequential read operations. Users are not concerned about the response time they process the data in bulk. Google has developed MapReduce programming model for meeting the fast-growing demands of their web search engine has developed Zing process. GFS system is used to perform the MapReduce computations. Google File System is nothing but clusters of computer. The cluster is formed by the networks of computers. Every cluster has thousands of machines. There are three main components in each Google File System, and they are chunk servers, clients, and master servers. The client makes a file request like retrieve the file, manipulate the existing file, and create a new file. The client can be a computer or it can be a computer application. We say that a client is a customer of the GFS. The master server works as a coordinator for the cluster. The operation logs are maintained by the master server. The operation logs contain the data of master cluster's activity track. There is a minimum service interruption caused due to operation log. GFS keeps very small messages sent and received by the master server. The chunk servers actually handle the data, not master servers. They are the workhorses of the GFS system. The 64 MB file chunks are stored in chunk servers. They do not send chunks to the master server. Client requests the chunk to the chunk server and the chunk directly sends the request chunks. Each chunk is copied by the GFS many times and kept on diverse chunk servers. Each copy is known as replica. GFS by default creates three replicas of each chunk. Users do not change in the setting and they can make the additional replicas as they wanted. Now let us discuss about Hadoop distributed file system. Hadoop is an open source framework developed by inspiring from the GFS and MapReduce success. It is it is used to build large clusters. HDFS use the distributed file system design. HDFS runs on a service hardware and is extremely fault tolerant. Hadoop file system earlier developed by the Google, but later on it became an open source framework. HDFS stores the large amount of data and it offers a faster and easier access. The data is stored in the file and the files are stored on many machines. The files are stored in a redundant way to protect the system from data loss in case of failure. Hadoop distributed file system prepares applications accessible to parallel processing. The features of HDFS are appropriate for distributed storage and processing. To interact with HDFS, Hadoop offers a command interface. It has two built-in servers called NameNode and DataNode. These servers assist the users to check the status of the clusters. It streams the access to the file data system. HDFS offers the file permission and authentication facility. The HDFS uses the master-slave architecture. The data node, name node, and the blocks are main component of the HDFS. The HDFS namespace contains the file and the directory hierarchy. The inode represents the files and the directories on the name node by inode, which records qualities such as access time, modifications, permissions, and disk space quotas. The name node is nothing but the service hardware. The name node comprises the GNU or the Linux operating system and the name node software. The name node software can run on the service hardware. The system which has name node is a master server. The master server manages the namespaces of the files. It regulates the file access. The file operations like renaming a file, opening and closing a file or directory are executed by the master server. The data node also has a commodity hardware, software, and the operating systems GNU or Linux. For each node in the cluster, there is a data node. These nodes accomplish the storage of their system. Data node, as per client's request, performs the read and write operations on the file system. Data nodes also perform the operations like creation of block, deletion, and replication of the blocks according to the orders of the name node. The user data is kept in the file system of the HDFS. The files are divided into one or more additional segments and are stored in separate data node. Segments are also known as the blocks. The blocks is the least quantity of data is written and read by the HDFS. The defaulting block's size is 64 MB. The block size can be changed according to the requirements. Now let's compare the GFS and HDFS. Though both the file systems are using master slave architectures, but there are several differences between both of them which are listed as on the basis of some criteria. HDFS works across several platforms whereas GFS is limited to Linux. HDFS was developed by Yahoo and it is now an open source framework whereas GFS was developed by Google. HDFS has two servers, namely NameNode and DataNode. GFS, on the other hand, has a master node and chunk server. Both the HDFS and GFS use commodity hardwares. In HDFS, writing once and reading can be done several times, whereas in GFS, it is a multiple read write model. In HDFS, the files deleted are renamed into a specific folder and after that file will be removed through garbage. Whereas in GFS, the deleted file is renamed in hidden namespace, it cannot be reclaimed instantly. The file will be deleted after 3 days if the file is not in use. HDFS has no network stack issue, whereas GFS has a network stack issue. For availability, HDFS has a journal edit log, whereas GFS has a operational log. Other operations possible in HDFS is only append. In GFS, random file write is possible. These were the differences between GFS and HDFS.